As Dr. Shatnawi told you, that I've got a lot of experience in this area of dealing with rubber. I did a lot of the research early on with Caltrans for asphalt rubber mixes, but I think one thing that's really been missing in some of the work that's being done by cities and counties and states is the use of multi-layer strategies. So I wanted to prepare a paper on just that subject and kind of show some performance history and the type of things that I've followed over the years dealing with multi-layer strategies. You've probably seen this before, but rubber is approaching a 40-year history. There's a lot of data out there. There's been a lot of work, but as we saw today and every day in here, we're learning more and more about these things and why they do what they do as we do more research. And I applaud the folks that are continuing that work. One of the things that in the early years, and this has been talked about a lot in previous presentations, so I'm not going to go through it a lot, but is there a point? Oh, yeah. The only thing I really want to point out here is that this, I think, is a very, very important chart. There was a study done in the early 80s that really opened the eyes of a lot of folks when you talk about dealing with rubber binders, asphalt rubber binders. And it was a study that looked at what effect does this crumb rubber have on the base asphalt, and how does it affect the properties that you have in like rutting and thermal cracking in a lot of these types of areas. But this is what's very important that I think that really illustrates why we're getting such great changes. And as you see the percentage of crumb rubber goes up, we get to about 10%, and we get a change. We get to about 15%, and the change in slope. But look what happens when we get up into this range, the 18 to 20%. A huge, huge change in the viscosity. And I think this is really the key in why we have the properties and the changes that we do, is because we found a number of years ago that the 18 to 20% range was maybe an optimum type point where you get to, if you get much above this, it becomes too stiff to deal with, but below that you may not have enough in there to make great enough change. So I think that's why we ended up where we are today at 18 to 20% crumb rubber. But a lot of the other studies that were done showed that there was a huge change in viscosity. The temperature susceptibility of the binder changed. We had changes in the thermal performance. We had changes in softening point, as showed earlier. We had changes in the repeated load creep, which shows you the effect of rutting. And you can see that there's almost a horizontal line with these rubber binders, which is quite a change from the slope of the conventional asphalt, which equates to the field. I've seen literally hundreds of projects, and I've seen very little rutting at all with many, many, many of these projects. And then the last thing is binder aging. And again, that's something that, well, really what's causing this binder aging to reduce and to resist the aging effects. And maybe for the first time we have an answer. So I like that. The uses, there's been a lot of uses, and I've reported on a lot of the performance of these different types of mixes that we've used. Dense graded, the early work that was done in California was done with dense graded mixes, performed very well. But as we got into the gap graded materials, which increased the binder content, we really moved away from dense and went to gap because we saw a much even greater improvement in performance because of the increase in the binder content. And then, of course, open graded, we also found a significant change there as far as performance goes. The other thing was chip seals. We've done cape seals. And last but not least is multi-layer systems. And this is something I've followed for many years, and I'm glad to be able to report how these systems can significantly improve and change the cost effectiveness of building projects in cities, counties, and interstates. These are the prime candidates for asphalt rubber. And every time I go give a presentation somewhere in a city or a county, maintenance of anything, I ask how many of you have city streets like this or areas that you have to deal with, and everybody in the room raises up their hand because we just don't have enough budget. We don't have a big enough budget, enough money in the coffers to take care of all these types of problems. But asphalt rubber really gives you the tool to be able to deal with something that is really eating up your money when you talk about what are the options to take care of a problem like this. Early in the research that Caltrans did, we looked at SAMMs, or stress-absorbing membrane interlayers, which is basically just an asphalt rubber chip seal. And we did a lot of work with SAMIs, and they were very successful, and they really made a difference in the work that we did. And I'm going to show you why and where those projects were. And I believe that really the key to multi-layer strategies is the use of the SAMI or the asphalt rubber chip seal as an interlayer. This is the reason why. This is a 13-year-old chip seal that's been exposed to the environment. I don't know of any other product that you could put on the roadway as a chip seal binder and go out after 13 years, dig the aggregate out of it, and physically see some stretch still left in that binder after 13 years. And I think this is why you get such great relief of stresses and strains in your pavement structure, because when you use a SAMI and an asphalt rubber chip seal in that fashion, it's going to take a lot of the resistance to the cracking out of your overlay and relieve it right there at that interlayer face. Here we see you can put down a one-layer system, but you add a chip seal to it. We've had some projects that are just phenomenal, phenomenal change in the performance by putting that chip seal underneath any type of product, whether it's rubberized on the top or conventional mix on the top. And that in the early work with SAMIs, we looked at both of these, and we found significant differences. Or we could go to multi-layer systems. Here we see a 3-layer system where you put a leveling course, the SAMI, and then AC overlay, or an asphalt rubber overlay. So early on, how did we really start looking at these things? Well, there was a project called the Ravendale Project. It's probably one of the most documented projects in California. We looked at it for about 16 years, but the research lasted about 12. Number of papers written on it. And really what we did is that we looked at different thicknesses of conventional mix and different thicknesses of rubber and combinations. This was up in the high desert on a state route, and it was put down in 1983. It had somewhere around 1,200 vehicles a day. It wasn't a real high-volume roadway, but it was in a snow environment. You did get some snow days, and you also got some chain wear on it, about 20 days a year. What we did on this project is when we first put the project out, it was going to be 4 years. We're going to look at this and evaluate it. Because we felt that we did a deflection study and found that the design overlay was 150 millimeters or 6 inches because there were extremely high deflections on this roadway. So what we did was build different thicknesses of the wet process here with and without a SAMI, and we used some dry process. We used different thicknesses of conventional, and then we used a single chip seal and double chip seal. So we expected that when these sections would start failing, we could compare them to different thicknesses, and we could kind of gauge how long these things are going to last. We had no idea what we were going to find. But we did easily predict, because of the high deflections and the condition of the pavement to begin with, that we would get early reflective cracking, and within 2 years, all of the thin sections of conventional mix, this is what they look like. This was at year 2. All the thin sections were very similar to this. Reflection cracking, there's a chip seal placed on this after the first year. This was the second year they went out and crack sealed it. We would expect this. But what we didn't expect is that in the rubber sections, the only crack that showed up in the first 5 years was this transverse crack across an area where there's a culvert. So we had to extend the life of the project 4 more years. Well, what did we really find? Well, the bottom line is that these are the rubber sections from the beginning. This is the 45 millimeters over a SAMI after 16 years. You can see here a crack going out, and it just disappears once it gets into the traveled way. You can see there is some wear on the pavement, but it's still actually in pretty good shape. You can see the crack in the middle, down the center where you don't get any traffic. You can see a little bit of transverse, some longitudinal cracking, as we see here. But for 16 years with 45 over a SAMI, looking at a 10-year design life, I'd say this is pretty good performance. But even more was the 75 millimeter over the SAMI after 16 years had 0 maintenance in 16 years. The maintenance folks in this region kept telling me, what is this stuff? I want to put it on every project that we build because we can eliminate the maintenance department. But it really showed us a lot from this early project. And here we can see the asphalt rubber section. This section had actually been rehabbed already, and you can see the cracking that is already reflected through it after 7 years. They finally had to overlay these sections after 16 years because the pavement on the end of each both ends of these test sections was to the point that they had to rehab it. So these sections were overlaid. So we don't know how long they would have lasted. But this here is the 75 millimeter. You can see the condition it was in. There was very little cracking, and again, zero maintenance after 16 years. So what this led us to do is, after the first 3 years, we realized that we could reduce the thickness of rubber and get the same design life or a longer design life. So in 1992, we came up with a reduced thickness design guide, and we went out and we built projects starting in 1992 with reduced thickness on every project, and I'm going to show you a little bit about that. But where did we use these projects successfully? I could show you many, many types of projects. And again, I reported on a lot of these before. We did overlays on bridge decks in the snow country, in the desert, both of these, a 21-year-old chip seal, interstates. This here was in the snow country. This project lasted 21 years. It was one of the first projects we built. I'd say that's pretty good life in the snow country with an overlay of concrete pavement. So these are the different types of products we're talking about, chip seals and gap-graded, dense-graded. Well, what happens when you put these things together? Let's look at some practical applications. We're going to look at rehabilitation versus full reconstruction. Really, what are the actual cost savings of multi-layer strategies? Well, we've done some work on some projects to actually show the physical savings, the actual savings in dollars. Here's a project in the very small city of Hemet. Option 1 was a standard overlay at a cost of $337,000. Option 2 was full reconstruction, 75 millimeters AC over aggregate base, cost of $824,000. The third option was a rubber overlay over a conventional mix at $263,000. They could not do option 1 because it was curb and gutter and there was too much of a crown on the pavement. So the only two options, they had to choose this one or this one. So they built this section, and they saved $561,000 on that single project. The project was a 10-year design. It lasted well over 10 years. So someone asked me, well, why would you use a little tiny dinky city of Hemet? And I said, well, think about it. Tiny city, tiny budget. How much is a tiny savings of $561,000 to a very small city? It's tremendous. Here's another project. This was actually a Caltrans project where option 1 was reconstruction of the pavement. And you can see they were going to coal plane, crack and seat, and then they were going, it was an overlay of, it had asphalt concrete on a concrete pavement. They were going to mail off the AC, crack and seat, and then put pavement reinforcing fabric and 75 millimeters of AC at a cost of $11,818,000. The contractor came to Caltrans and said, well, okay, let's put this 3-layer system in here. We'll cold plane 85 millimeters, put a SAMI down, put an overlay of rubber, and then finish up with open graded on the surface at a cost of $7,343,000, or a savings of almost $4.5 million. Unfortunately, Caltrans made a decision that they didn't want to do this. Now, I'm going to show you why I think that wasn't a very good decision. But this can show you the tremendous amount of savings that these things can afford an agency. The question is, are they going to perform? Well, let's look at some of these 3-layer systems that I've followed for many years, and you saw this slide earlier. This is the actual construction costs of a project, Randolph and Enterprise Street. Option 1 was full reconstruction. You can see what it is there. Option 2 was a 3-layer system. And you can see the two costs here on this project. There were only 2 city streets, but there was a $52,000 savings in the project for a 10-year design life. This is what the project looked like. Not very good. There was nothing done in here except they put a 1 inch or a 25 millimeter leveling course. So right in the center of that pavement was probably a little bit thicker, but they leveled it up. They put a chip seal as a SAMI, and they put 37 millimeters of gap-graded mix. This is at 10 years of service life. There's not a crack in the pavement. Well, this year, I went out and took some pictures because they're 15 years old this year. And this is the same exact location, 15 years, and there's not a single crack in the pavement. Now, this particular area doesn't get a lot of traffic, but still it illustrates where you can use these types and what kind of actual savings you can get. This was the other street. You can see the alligator cracking, some potholing in here. Again, they used the same strategy. 10 years old. There was a few cracks in an area here that was a water problem. Here it is at 15 years. There was actually a slurry seal placed on this 2 years earlier, but there's really nothing in the pavement really to talk about other than a few spots that they had to remove and replace because of a standing water. But these are two that I followed for 15 years, and the performance is really pretty phenomenal. This is the other project that when this was done, I said, well, I just don't know, you know. I mean, look at this. These are very wide cracks. There was concrete pavement down under here initially. Years and years ago, there was an old trolley that ran down the center of the street. The rails are still underneath the pavement. So they had been overlaid a number of years, and that's why you see the large block cracking, because there's a lot of stresses going on in there because of the concrete pavement down below. So the same thing was done. Oops. Same thing was done here, same strategy at 10 years. You can see a crack here. There were a few cracks I saw at 10 years. Here it is at 15 years. You can't see the pavement very well from the same picture, so I turned and took a picture down the roadway. You can see there is some cracking, transverse and longitudinal, but it was pretty minimal. And again, this is 15 years of life. This is in Los Angeles. They get a fair amount of traffic on this street. And I followed that and pretty much watched it almost every year. This is another project on a multi-layer system of just 2 layers. And the city of Ventura came to the contractor and said, all right, this rubber stuff you're talking about is so good. Well, I'd like you to give me a 10-year maintenance-free warranty. So the contractor had a lot of experience with this product and had a lot of confidence in it. He says, fine, I'll give you a 10-year warranty. This picture was taken at 10 years. There was an asphalt rubber chip seal placed as a SAMI with an overlay of 45 millimeters. At 10 years, there was no distress, no cracking, no maintenance. Now, what was interesting is at that time, the contractor when he placed the chip seal, he said, let me just spray a little bit on the pavement up ahead. I didn't see you walk up. And we'll see how that performs over a period of time. And what he did is, you see where he sprayed it here, and actually this line should be back here because you can definitely see the outline of the chip seal. If the chip seal has resisted the cracking for 10 years, how long do you think that this is going to last with 45 millimeters of rubber mix on the top? I'd say it's going to last quite a while. I'd predict probably something in the neighborhood of 20 plus years. But you can see what happened to the pavement around it. And when this overlay was placed, there was hairline cracking like this everywhere, but you can see what happens. I like to use this in my preventive maintenance presentation because it shows what preventive maintenance can do. But really, you can really see the effectiveness of the SAMI here in just a 2-layer system in a city. I'm going to get closer here in finishing it, and what I want to do is show you in thin layers how well just a thin layer of asphalt rubber can perform, because I think it says a lot about the product. There was a project placed farther down that had a chip seal on it, and it had some hot mix. So the contractor said, why don't you let me come into this area right here. You can see all the distress. It had alligator cracking, longitudinal, the potholes. And let me put some of this material down, and we'll just watch it for a while. Here's the picture taken after 1 year. 25 millimeter overlay of gap-graded mix. Right there it is. Now watch the areas surrounding this. This is at 5 years. Look at all the cracking. It's over here too. It's just hard to see in the slide. You can see some of it there. No cracking in this 1-inch overlay. This is after 10 years. Look at the extensive crack and extensive crack sealing. There wasn't a single crack in the 1-inch overlay. I think this right here really says what asphalt rubber can do, and especially in thin layers. And that's why I think that when you build thin multi-layer systems, they perform so well. The pavement is flexible. Even though you have very high deflections in an area, that thin section can tolerate extremely high deflections without, number one, oxidizing, without cracking. It protects the pavement because water can't get through. You've got an asphalt rubber chip seal to protect you from water intrusion. So one of the things that was looked at in these projects that I showed you earlier at Randolph and Enterprise Street was the normal theory would tell you that over a period of time your base continues to break down. Well, that's because water gets in there and continues to work under traffic and the base breaks down. What was found on these streets, they did some testing of the underlying base, and they were very surprised in what they found, that the underlying base, because it had been kept dry from the intrusion of water, the breakdown was not near as what it would be expected. And they thought they had bum tests, but then the more they thought about it, it really makes sense that if you protect your base from water intrusion, it's going to break down at a much slower rate, even though you may have higher deflections. And this here, I think, is again a 25 millimeter overlay. We have this core still in our office in Chandler, Arizona. But what's interesting is this crack, that it looks like there's a crack on both sides. And this was at least a 25 millimeter crack that was in the pavement. And this pavement core is intact. It hasn't broken and fallen apart. This was taken after 2 years of service life. But if you go back in the summertime and try to find these cracks, they won't be there because they heal up. And a lot of times when you see cracks in the surface, they don't go all the way through the pavement. If this crack did go through, this core would fall apart. And I think that's why this material heals itself like a lot of people talk about. It's because of the properties of the binder. It stays very flexible over a very long period of time. And what happens is it allows these cracks to be kneaded back together by the traffic. And hence you get a longer life. So the advantages is, again, you get higher abrasion resistance, reduced oxidation, increased fatigue resistance. You can reduce the thickness, that's proven fact, over time. Reduce construction time, this is very important. Exposure to the traffic, exposure of the traffic to the construction site. But the last three, I think, are very, very important. And these two do not get talked about a lot. In these multi-layer systems, the increased safety, because full reconstruction is a very long period of time, months in some cases, whereas placing multi-layer systems can be just weeks. The other thing is savings in energy and natural resources. In California, we every year are more and more concerned about our dwindling aggregate sources. And quality aggregates are being more and more less prevalent in the state because we keep covering up our aggregate sources because we keep building out, and so they become more valuable. And if we use these multi-layer systems, you can significantly cut down on the thickness, which these two issues are energy and safety are two very important issues. The last thing is lower maintenance costs. So what are the advantages of multi-layer systems? Well, the asphalt rubber and chip seals have a proven performance history just in their own performance by themselves. We know they can tolerate very high deflections through the projects we've placed. So these multi-layer strategies on the projects that I've followed, and there's a number of them out there, I just shared some with you, show that there's a very proven performance with them. And the big thing is down here in the cost savings that you're going to achieve, and the savings in energy and natural resources. The recommendation is agencies should become more educated in the selection, design, and construction of multi-layer pavement strategies. They should use more of these systems so that they can stretch their maintenance and rehabilitation budgets. And as you can see from some of the cost analysis that I presented, savings can range from thousands of dollars to millions of dollars, which allows you to do a lot more with the distressed pavements that you have in your local areas. So I hope you enjoyed seeing what multi-layer systems can do, and thank you very much.
Do you have any questions for Jack?
My impression from the 2 days is if you use asphalt rubber pavement, you're going to reduce the maintenance cost, but although you have a higher initial cost. But from you have shown, you not only have a lower maintenance cost, you also have a smaller initial cost. Is that right?
That's correct. The reason is the reduction in thickness. A lot of agencies do not reduce the thickness. They're using equal thicknesses. There's two ways to look at it. You can put it down the same thickness and get an extended life, much extended life, or you can reduce the thickness and either get the same service design life. But what we found is we, in fact, even though have reduced them, we've learned that thin layers of the product perform very well. And the initial costs, the higher initial cost per ton or unit cost of the mixes is offset by the reduction in thickness. So as you can see on these examples I've given you, just about every case that I've seen, there's been a savings. Because when you talk about reconstruction, there's a whole slew of issues that come in there that really aren't even up here. User delay costs aren't even considered in this. But really, the effect that it has on businesses around those areas and the traveling public is tremendous. So they're extremely cost effective.
Thank you.
Jack? Hello?
Any other questions?
For those of us that weren't able to go to the other session, could you give us a couple quick bullet points as to key construction issues?
Yes, I could. The three most important things in construction are temperature, temperature, and temperature. That's no kidding. One thing is the aggregate. You know, you need to have good quality aggregates. You have a high crush material. Because you're reducing the thickness, you have to have a stronger structure to begin with. It's rock to rock in the gap-graded mixes. In the construction, you're going to have a little bit more difficult time compacting these mixes. You're having more trouble getting VMA during the mix designs because of the way that the structure goes together. But you want to guarantee you have that so you don't fill up your voids. Construction is you got to keep the material hot, place it, get it compacted before it cools down. If it gets cooled down below 290 degrees, you're going to, below 270 to 280, depending on the ambient and surface temperatures, you're not going to compact it. So you need to get on it when it's hot. The other thing is that the handwork that's done with this is you don't have time to move it around like you do conventional mix, because as it begins to cool just 10, 20, 30 degrees, it becomes very stiff. So you'll find that the contractors learn that when they get out there, they place the material. If they're got to do any movement in this material, it's done very quickly. We initially started out with a maximum temperature of 350, but we had problems with fumes of the base asphalt. So we lowered the temperature down to 325, which is the same as it is for conventional mix, and we're able to place the product. Cool weather, where you have like a coastal area where you may have fog, or you may have dampness, or the surface temperature, ambient temperatures are below 50 degrees. It can be done successfully there if you have extremely good construction practice. We originally raised the temperature from 50 degrees Fahrenheit to 55. So the main thing, the main thing is the temperature. And what we found, I've been involved in two evaluations. We did one in 1995 of all the projects that had been built by Caltrans up to 95. And then in 1999, we did a follow-up of that. We changed the what we found in the first one was that we had a lot of problems due to temperature. If you don't get the mix compacted, it'll ravel, it'll crack, it'll start to spall. If they're compacted and placed properly, there's a very high percentage chance that you're going to have a successful project. So temperature is so extremely important, and compaction. So, and the air voids, the other thing is the air voids in these mixes, I've seen a lot of mixes that have gone down that have very high air voids in them, above 13%. But yet we get over 10 years of service life from them. So the more you get them compacted, the better you get them compacted, the longer they're going to last. If you need any other information on that, I'd be glad to send you something. Caltrans has a RAC user guide. RPA has a RAC user guide. They're both very similar. They tell you everything you want to know about working with asphalt rubber. So that would be a good tool for you. You can get that on their website, the Caltrans website. We had one more question?
Right, it's right here. I have a quick question. You mentioned this system is relatively, resistant to fatigue. And you mentioned that it's relatively soft. So have you seen any rotting problem, especially in hot areas, even though it looks like the project were done, didn't get that much traffic? What about, under significant amount of traffic and hot area? Did you see any rotting?
No, again, This product is a very stable material. I've seen very few rutting projects. I've probably seen literally hundreds of projects, and I could count the projects that I've witnessed rutting on those jobs on one hand. Now, I'm not talking about rutting at a stop bar or rutting where a bus comes in. I'm not talking about those types of areas that we're going to get rutting problems with any type of product that's placed, unless you put something like concrete in those areas. But the rubber mixes have a much higher resistance to rutting, even though when you say softer, I don't recall using that term. I would not call these softer mixes. They're very, very stiff mixes because of the high viscosity. They may have softer properties when you look at them from a standpoint of flexibility, but they are a very stiff mix. Did I answer your question? We had one right over here.
I heard that more than once, that you don't have to come up with the same thickness. You can come up with end up with a smaller thickness, even with a 3-layer system.
Mm-hmm.
I assume that the traffic will continue to inflate when we have the same traffic. Are we violating any pavement design principles as far as the overlay design?
Yes, we are.
Okay.
And I'm glad you brought that question up because it's very dear to my heart. When it comes to talking about the design of asphalt rubber overlays and structures, common wisdom or common overlay designs used for conventional mix do not really work with rubber. There was a presentation given earlier that I had some comments on that kind of indicate what that means. And there's been another presentation that was given on the ALF that showed exactly the opposite in actual field performance. The thing is that in common theory, in conventional design theory, you want to have a very stiff, high-structured base, and you put an overlay on it to protect it. And the thickness is determined by the rigidity and the deflection level that's in that pavement. Whether you have a sub-base that's very weak, it's going to be stiffer aggregate base, thicker aggregate base, thicker overlay. But in these rubber systems, the deflections, you can't think like you do with conventional mix, because I'm not concerned about deflections because of what I've seen. And the study that was done, I told you about, where they went down and they tested the base. Again, you put a SAMI in there, you don't get water in the base, you protect the base. So the base breakdown is at a much slower rate, even though you're at a higher deflection level, which violates what you're doing. And in California, when we did these, we would go out and run a deflection level, determine the thickness, and if you look into the Caltrans website or their rehab manual, you'll see it's just strictly a reduction in thickness. And it's very conservative, but the reduction is up to 50%. I personally believe you can go much higher than that, and I think these multi-layer systems tell you that. But there currently is no design philosophy other than let's put something down and try it. I mean, I've seen thin layers of 25 millimeters, a SAMI, and 25 millimeters perform well over 10 years, where you might have a very thick overlay was recommended because of deflection level.
So there's no design methodology?
No, I think that's something that is evolving now. I mean, I'm glad to see work being done. There's a number of folks that are doing some work with the rubber mixes, but I think you got to be very careful not to jump the gun when you look at conventional wisdom and try to say, well, because you have these certain parameters of high deflections or whatever it is, we can't use rubber overlays. Because if you see these projects like I've showed you, I've watched these jobs for many years, many of these projects, and it just baffles your mind when you think about a conventional design philosophy. So yes, they violate a number of areas. But to me, field performance is more important and more valuable than anything you do in the lab or anything more than somebody's opinion. And that's what I really have looked at over the years is field performance to get, I think, where we are today with some of these products. Any other questions?
Right here. Considering that temperature affects the stability of the rubberized pavement once it's paved, in your experience, at what temperature should the recently paved surface should be open to traffic?
You mean, what temperature should the mix get to prior to opening it to traffic?
Correct.
I would say it's somewhere in the neighborhood of 160 degrees. It's still similar to conventional mix, but because it's a gap-graded mix, this product will cool a little bit faster. But it's still more stable, so you could probably go even higher with that, 170 degrees. But what we've done in the past is we've treated it like conventional mix as far as temperatures go, opening it to traffic. One thing you have to do, though, is you have to either spread some sand on it to begin with, very light, something around let's say a kilogram per square meter or 2 pounds per square yard, because the rubber particles will stick to the tires. Tires get very hot when they're rolling on the road, so you can either use a lime water, you can put a bag of lime in a trucker and spray water on the pavement. As long as you get some kind of film on the surface to keep it from picking up, you can open it to traffic. The water works good too for the other reason of lowering the temperature, but in California that's probably not an option because of putting lime down a DI, or you might kill some three-eyed salamander or something, I don't know. So. But did that answer your question?
Yes, thank you.
One other thing, the gentleman next to you, in his question, I failed to answer one part of that, and that is, how about temperature extremes with hot pavements? These types of materials have been placed in very, very hot climates, in desert regions, low desert, and have performed very well without rutting because of the increase in the softening point.